So, welcome everyone to Guided Study Group Week 4 of my 141. And so today I'll be going over the last 3 sections of integration, the materials for midterm 1, which is 7.3, 7.4, and 7.5. 7.3 is mainly about trig substitution, where 7.4 is mainly about is partial fractions, and then 7.5 is kind of like a summary of all the strategies and technique that we learn in integration and how we can apply them for different type of problems. And there are cases where we have to use at least 2 techniques to solve them. And so first thing is 7.3 trig sub. Trig sub is when you do the substitution in the form of x equal to g theta, where g can be one of the trig function of sine, tangent, and secant, assuming that g has its inverse exists. So say in the cases of where you have definite integral, where you have the boundary from a to b of, say, some function of x. Then when you do the change a variable of x from a to b to theta, then your theta have to satisfy these conditions of the substitution. So, but usually in the case, you guys gonna see the indefinite integral of the function. And so when you have things like square root of either one of these form, it's kind of like a sign where you can do the substitution, but sometimes it's very, very subtle. And so what you're going to do is that we will try to first put these into this form. And how do we do that? Usually it can combine U substitution and trig substitution. So instead of just saying, say, things as easy as 2 squared minus x squared, usually you're going to have 2 squared minus x plus a squared, where a can be any kind of constant. And so that is where you have, that's when you have a complicated case where you have to use both U substitution and trig substitution. So you put this as U. And then finally, when you do all the substitution, do all the integration, finish the integration, kind of like solve the integral and get the final answer in the form of theta, then you have to use the right triangle formula to get back to x. And that will be our final answer. Remember that when you get into theta, that's not our final answer. You get no credit for that because there will be no answer choices that show you the integral in the form of theta. It has to be in the form of x because our initial variable is x. And this is usually the cases that you're going to see an indefinite integral, not a definite one. So let's go to the first example. The first example asks us to find the integral of 3x over square root of 3 minus 2x minus x squared dx. And so here we have, I'm going to try to put it in the form of x, in the form of any kind of a squared minus x squared, a squared plus x squared, or x squared minus a squared with that square root. And so here I'm going to try to complete the square here because I feel like if I complete the square, I'll see something. So here we have 4 minus 1 minus 2x minus x squared dx. And then we have this part is when you take the negative out, you're going to have x plus 1 squared inside. So the square root will become x plus 1, 4 minus x plus 1 squared dx. And so now this is where I'm going to use the U substitution. So here we have a squared minus x squared. You're going to do the substitution. It's side, but first you're going to try this. u is equal to x plus 1. Then you have du is equal to dx. Then this integral will become 3u minus 1 du divided by square root of 4 minus u squared. Now, when we do the substitution, you have u equal to psi theta. Because now your a is 2. This is 2 squared. And so you have du is 2 cosine theta d theta. And so your integral will become 3 2 sine theta minus 1 2 cosine theta d theta divided by square root of 4 minus. So now one of the things that I forgot to mention is that one of the you also use sine square plus cosine square equal to 1, and secant square plus 1 is equal to tangent, or secant square is equal to tangent square plus 1 equal to 1 over cosine square. These are the additional relations that you guys are going to use to solve this type of problem. And so what we end up having is that we're going to have 4 minus 4 sine square, which is going to be square root of 4 cosine square. So it's 2 cosine theta. So now we only have 6 sine theta, because these two cancel out. And so you have 6 sine theta minus 3 d theta. Putting them back, now taking the integral, I'm going to have negative 6 cosine theta minus 3 theta. And so here, now we use the right triangle formula that we learned last week, in the last few weeks, to solve the problem. And so here we have, let's see what we put. We put sine theta equal to u over 2. So this is theta, then this is going to be u over 2. And then your u is x plus 1. So this sine is going to be 4 squared minus x plus 1 squared, which is going to be exactly as our denominator. It's 3 minus 2x minus x squared. And so this is also one of the way that you check your final answer when you do trig substitution, is that when you use the right triangle form relationship to put back into x, at least one of the sign is going to equal to one of the phrases that you have in the initial integral. So say in this case you have this square root of that. So in your answer choice and 3x. So in one of the right triangle relationship, you're gonna have one of the sign is gonna equal to square root of 3 minus 2x minus x squared, or you're gonna have one of the side equal to x, and that's we don't know. But if you say here if you have one of these side that equal to square root of 3 minus 2x minus x squared, then this is one of the way that kind of let you check your answer that this is correct. And so here, what we have is now we're gonna have negative 6 cosine of theta is adjacent divided by hypotenuse. So you have square root of 3 minus 2x minus x squared divided by 2 minus 3 theta. So theta you can write as inverse sine of x plus 1 over 2, or you can write as inverse cosine of that, or inverse tangent. You can write anything you want, but I'm just going to keep my initial substitution, which is negative 3 inverse sine of x plus 1 over 2. And so here you can kind of like further simplify it into -3 instead of -6/2. And this is my final answer for this problem. Again, if you have any kind of questions when you review this video, please feel free to email me and kind of like tell me what happened. I might not be able to check my email that regularly, but I'll try my best to answer your questions whenever I see it. And then we have example 2. So this is kind of like an easier one when you already have the numerator put in the form of x squared minus a squared under the square root. And so we're just gonna go ahead and do the substitution now. We're gonna put x equal to a here is equal to 5 because 25 is 5 squared. So you have 5 secant theta. Then you have dx is going to be 5 secant theta tangent theta. And so this is where you look the derivative and integral of trig function becomes important, as I mentioned last week. So if you forget this part a little bit, please review the table last week where I have kind of like a summary table where you have all of the trig function and derivative and their integral. Excuse me. Now you have your integral equal square root of 5 secant 25 secant square minus 1. Dx is 5 secant theta tangent theta d theta divided by 5 cube secant cube. And so in the square root, what we have is that we're going to have 5 secant square is 1 plus tangent. So secant square minus 1 is going to be tangent square. And so under the square root, that's what we're going to have. 5 tangent theta times 5 secant theta tangent theta d theta divided by 5 cube secant cube theta. So to kind of like simplify the problem, what we're going to have is that it's going to be tangent square theta divided by 5 secant square theta d theta. Now this is kind of like a deadlock for us because we wouldn't know where to go from here. You can try different ways, and usually when I'm coming to tangent and secant, what I'm usually just gonna do is that I'm gonna put it back into the form of sine and cosine because it usually works for me to solve the problems. And so the way I'm gonna put it is that tangent square is sine square over cosine square, and then in the denominator secant square is 1 over cosine square. So 1 over cosine square cancel out. So what I only have left is sine square over 5. And now I can easily use the double angle integral to kind of like simplify this. So we have cosine 2 theta is 1 minus 2 sine square theta. And so this one is going to be multiply 1 minus cosine 2 theta d theta. And so after that, I'm just gonna solve the integral, which is going to be theta minus 1/2 psi 2 theta. Again, we're gonna use the right triangle relationship to put it back into x. So this is theta. Your secant theta is x over 5. So secant is hypotenuse divided by adjacent. So it's x over 5. And then so this side is going to be x squared minus 25. Again, this is kind of like the part that kind of like confirm our final answer that it is correct. And so now I'm just going to put it back. So theta is inverse secant of x over 5 minus 1/2 sine 2 theta. And now Now this part is kind of like a little complex because sine 2 theta we cannot represent by the right triangle relationship. From the signs, from the like trick of theta, we cannot really say anything about sine 2 theta. So we have to use a double angle, half angle relationship to put it back into the form of sine theta and cosine theta because we cannot solve anything about sine 2 theta. So this is going to equal 1/10 secant of x over 5 minus, now inside we have minus 1/2 multiplied 2 sine theta cosine theta. And so it's going to be 1/10 of sine theta is square root of x squared minus 25 over x. Multiply cosine theta is 5 over x. And so this part is just going to be 1/10 inverse secant x over 5 minus 1/2 square root of x squared minus 25 over 2x squared. And this is my final answer for this problem. And so in this case, the important part in this problem is that when you use trig substitution and you have sine 2 theta left or cosine theta left, after you solve all the integral, it's really hard for you to go from this triangle and derive what is cosine of 2 theta and sine 2 theta if you just like draw this part a little bigger and then solve for what is 2 theta. But using the half angle formula, it allows us to find what is the actual value of cosine 2 theta and sine theta after you already solve the integral. And so having said that, that's all I have for example 2 and section 7.3. Now we're going to move on to section 7.4, partial fractions. And so partial fraction is that when you have the rational function in the form of px over qx. These are two polynomials, but we can only use partial fractions, kind of like this kind of technique, when you have the highest degree in p is smaller than the highest degree in q. And when we don't have this, this is what we're gonna happen in the next slide. When it's not in that proper form, then when we have to use long division of polynomials. So say divided the numerator by the denominator until the numerator have the highest degree in the numerator. The highest degree in p is smaller than the highest degree in q. Then we can use partial fractions. So the first step is fully factor the denominator. After we make sure that it's proper, we fully factor the denominator. Set up the fractions. So say if you have px over only x minus a times x minus b times x minus c in the fractions, then we put this one in the form of a equal 1 minus b over x minus b plus c over x minus c. Then if we have some sort of irreducible quadratic, say you have px over x squared plus ax plus b times x squared plus cx plus d. Then you put it in this form. If you have repeated linear factors, so say you have px divided by, say, x minus a squared times x minus to the n, then x minus b, then you put it into this form and repeat it irreducible quadratic. So when you have a quadratic to the n that you cannot reduce it into a square, and then you multiply x and you have x minus 2, then this is the form you're gonna put it. Now this sounds a little bit too complicated, but this is the kind of like the general rule. It doesn't seem to be any kind of exception to these formulas, so it's really easy if you just follow these formula and try to solve the problem. And so the next step is you equating both sides to find what is a, b, and c. And I'll make it clearer in the example. and then you're just gonna integrate. So let's do example 3 to see how it goes. So the first thing is that I try to show you guys how to use long division to kind of like put it into the proper form of polynomial. And so what we have is that we're gonna have 2x third plus 3x squared plus 7x plus 8 divided by 2x plus 1. Note that if you're missing any term in this, say you have power 3 to 2 to 1 to 0. But if you're missing any power in between, just leave that blank there, but do not fill it with, say, put a plus a over here, because it's gonna confuse your division. Now, how you do division? You have two. You're gonna use the highest power over here on the left to divide by the highest power on the right. So you have 2x third divided by 2x is gonna be x squared. So this one is gonna be. So when you multiply x squared with 2, so the next step is you multiply x squared with 2x and move to this side, but you change the sign of the value. Say if you have x squared multiply 2x, here you have 2x third. Put it over to the side, you have to change the sign. Similar to when you have like an equations and you put one term on the left and one term on the right. You have to change the sign of that. Same thing, you have x squared multiply 1 is x squared. And you change it over here is minus x squared. And then you don't have any other term. So then you have is going to equal 0 plus 2x squared plus 7x plus 8. Now this power is still higher than this, so we continue to do what we just did. So 2x squared divided by 2x is x. So you have negative 2x squared negative x. So what we have now is 6x plus 8. This two power is still equal to one another. It's not smaller over here. And so we will continue what we just did. So plus 3 minus 6x minus 3. So it's going to be 5. Now this is power 0 and this is power 1. And so that's the end of our long division. And so this long division now equal to x squared plus x plus 3 plus 5 over 2x plus 1 dx. And so this is a very easy integral for us to do. So I'm just going to do it quickly. X squared over 3 plus x squared over 2 plus 3x plus 5 over 2 ln of 2x plus 1 plus c. And so what I try to show you in this example is how to do long division and how to know where to stop. And so if you have any questions, because this is the way that I was taught during high school and secondary school in Vietnam. And so the way I present the division may be a little bit different from what you guys learn in the US. But the general idea is the same thing, is that we try to divide the higher power polynomial by the smaller power polynomial so that we get the rational fraction into the proper form, where you have a numerator here have the smaller highest power compared to the denominator. And so that's example 3. Now we're gonna go to example 4. So here we look at the rational fraction. It's already in the proper form, where you have this highest power in the numerator is power 2 and here's power 3. And so what we're going to do is that we're going to go ahead and factor the denominator. So we have 3x squared plus 7x minus 2. Denominator, if I take x out, what we have left inside is x squared minus x minus 2. And by doing a lot of practice, I know that the denominator can be further factored. So I will further factor it, and what I have is x minus 2 times x plus 1 dx. Now, as you can see in the denominator, we only have linear factor and none of them are repeated. And so, this case, we're going to have 3x squared plus 7x minus 2 by the form that I put in the slide of section 7.4, we have this one is going to equal a over x plus b over x minus 2 plus c over x plus 1. All now we're gonna try to put them in the same denominator, which is x times x minus 2 times x plus 1. Now in a, you only have x in the denominator, so you have to multiply the other two linear factor. So you multiply that by x plus minus 2 times x plus 1. Plus b, doing the same thing, you have bx, x plus 1, plus c, x minus 2. Now we can ignore the denominator and try to equate these two sides. So that is the third step in this section, where you use partial fractions. We have 3x squared plus 7x minus 2 is equal to a, x squared minus x minus 2 plus b, x squared plus x plus c, x squared minus 2x. And so now we're gonna put every term of x squared in together so that we can equate it. You're gonna see this in a moment. So you have put everything with x together, everything with x squared together, and every constant together. So you have a plus b plus c plus x. You have negative a plus b minus 2c, then negative 2a. So if you can see here, as you can see here, you have a plus b plus c is equal to 3. So kind of like the coefficient. What you equate is the coefficient in front of these terms. So in front of x squared on the left, you have 3 is the coefficient in front of x squared. On the right, you have that coefficient be a plus b plus c. So when you equate the two sides of the equations, you have a plus b plus c is equal to 3. Similarly, if you do negative a plus b negative 2c, this is the coefficient in front of x. That is going to equal to 7. And then you have negative 2a is equal to negative 2. So if you want to kind of like put it into different smaller and smaller fractions, that is on the point. So kind of like solve for what is a, b, and c. So that's on the point of partial fractions. Then solve this linear system and solve for what is a, b, and c. So here I have a equal to 1 from the last equation. And if you continue to solve the other two equations, then you're gonna have b is equal to 4 and c is equal to negative 2. And so from that, I can put this one as, so the integral will become, so I'll call this I. So I will become the integral of 1 over x plus 4 over x minus 2 divided by x plus 1 dx. And so now this is easy to solve. So you have ln of absolute value of x plus 4 ln of absolute value of x minus 2 ln of x plus 1 plus c. Or if you want to further simplify this, I can put it in the form of ln of absolute value of x times x minus 2 to the 4th divided by x plus 1 squared plus c. Kind of like using the property of the log function to kind of like further simplifying this algebra. So this is kind of like just algebra from now on. But when you go from here to here, that is the important part of this section. So again, I would say do all the suggested problems that Dr. Kasha gave you on Canvas. They're really, really helpful in kind of like familiarize yourself with this kind of technique, because I'm pretty sure that you guys haven't learned this tricks up and partial fractions in high school at all. And so that's all I have for section 7.4. So now I'm gonna go to section 7.5, which is the final piece of materials before midterm 1, strategy of integration. So this is kind of where we put everything together and kind of like do a lot of practice and try to use different techniques to solve the problem without knowing the fact that, okay, you're gonna use that. So this is kind of like where you go screwing in the dark because you look at one integral and it doesn't quite fit in many of the format but you have to figure out how to solve it using at least one of the technique. So as I say, this is hard in the sense because there are problems where you have to use more than one technique to solve it, kind of like similar to trig sub where you have to use trig sub at the same time with u sub. So the first step you're going to do is try your best to simplify the integral or look for the obvious integration. So if you can see easy use it. If you can simplify the algebra, do it. Then if you see log or inverse trig or combination of any two types of functions. So again, this sounds similar. This sounds kind of like familiar to us because when you have two different kind of functions, it's kind of the sign that shows us, okay, you're going to use integration by part. And so if this still doesn't work, then if you see the integral in the form of sine to the m, cosine to the n, or tangent to the m, secant to the n, that's when you use trig integrals. And those are the materials that we learned last week. Then if you see these form of the trig substitution, so that's 7.3, then you can use trig substitution and u sub. And sometimes you need something else like the one that I said, sine square plus cosine square is equal to 1, or secant square is equal to tangent square plus 1, things like that. Finally, if you see a rational function and determine if it's proper or improper, then you use partial fraction or not. Now note the fact that partial fraction is quite tedious in the algebra form and you have to solve. So you have to solve a linear system. Before that, you also have to put it into the same denominator on both sides of the equations before you can equate them and construct that linear system. So it's a lot of algebra and you can easily make some mistake. So in some cases, if you first think of partial fractions, you should also think of the way, okay, is there any other shorter way to do it? Because dealing with algebra is not hard but kind of annoying, and you can easily make mistake if you're not like a very good bookkeeper. So be careful with that, and I'll show that in the example. And you can also see that in my practice problems where in some cases partial fraction is not the best way to solve it. One thing to always remember, choose the simplest and fastest way. Again, dealing with a lot of algebra or going through a lot of steps increase your chance of making mistakes in between, and it make it harder for you to track your work when you do it in the exam or quizzes and kind of like go through and check your answer. You may need to combine several techniques. So please forget the idea that, okay, I will only do one substitution or one kind of technique to solve these problems. At this stage of the class, you should be able to use at least more than one technique to solve the problem, because that kind of like show us that you have kind of like a mastery of the material. And so having said that, I'll go through two examples where you use maybe like more than one technique, or in some cases, you don't need to oversimplify the problems. No, you don't need to overcomplicate the problems to solve it. Sometimes it's really easy, and you just mainly use what we learned before and kind of like maybe even like the double angle formula or half angle formula to solve a problem. And so the first thing when I look at it is that it gives me a rational function. So the first thing coming to mind is partial fractions. But looking at this, is there any way that I can make it simpler? Well, there are two ways that you can think about it. If you try to make it simpler, you can try to do plus and minus something. Say you had write this one at x squared plus 1 plus 2x minus 2 over x squared plus 1 square dx. And so this one can equal to 1 over x squared plus 1 plus 2x minus 2 over x squared plus 1 square dx. And so looking at this, it doesn't really help me solve any kind, because here you still have that quadratic part in the denominator, but it's not in the simplest form that we can continue to use like simpler integral to solve it. So this part doesn't really help. So I'm going to use partial fraction here. And so if you look at the denominator, it's fully factored because x squared plus 1 is always positive. You cannot further simplify it into, you cannot further factor it. And so what I do is that I'm going to try to use the formula. So here you have one linear factor and the square of a quadratic polynomial. So this is going to equal to a over x plus bx plus c over x squared plus 1 plus dx plus e over x squared plus 1 square. And so this one dx. Now saying that, what I'm having now is that I'm trying to put them in the same denominator. So I'm gonna have x squared plus 2x minus 1. I don't need this part. Over x squared plus 1 squared. This is going to equal to a x squared plus 1 squared plus bx plus c x squared plus 1 plus dx plus e multiply x. And so now I'm going to equate two sides. I'm having x squared plus 2x minus 1 is equal to, now I'm going to put every equal power together and solve the problem. So you have a x fourth plus 2x squared plus 1 plus bx squared plus x cx x squared plus 1 plus dx squared plus ex. And so this one is, I'm going to put everything with x squared together, everything with x squared together, and everything x together, including every constant together. Now I have a plus b plus x c x third plus x squared, then you have 2a plus b plus d plus anything with x, then we have c plus e. Then constant is just going to be a. Now, when you equate them together, this is a little bit more complicated because now we have 5 variables. And so when you solve for it, be very careful about algebra mistake. So you have a plus b. There's no x fourth on the left, so it's equal to 0. C is equal to 0 because there's no x third on the left. 2a plus b plus d is going to equal 2. Because that coefficient is equal to 1 because the coefficient of x squared on the left is 1. Then you have c plus e is equal to 2. And a is equal to negative 1. And having said that, then we can have a is equal to negative 1, b is equal to 1, c is equal to 0. And then when you continue to solve continuously for d and e, what you end up having is that you're going to have e is equal to, e is equal to 2 and d is equal to 2. So our integral I is now going to equal negative 1 over x plus b is 1, so c and c is 0. So you're going to have x over x squared plus 1 plus 2x plus 2 over x squared plus 1 square dx. And so now we're going to solve them individually. So again, I'll write up one bar. So we have negative 1 over x plus x over x squared plus 1 plus 2x plus 2 over x squared plus 1 square dx. Now this part is easy. Now you have negative 1 ln of absolute value of x plus this part is when you're gonna use u substitution. So if you put u as x squared plus 1, you can see that if you put u at x squared plus 1, then you can easily see that du is equal to x dx. Then you're gonna have this one equal to half of ln x squared plus 1. Now what we have left is 2x plus 2 over x squared plus 1 square dx. And so in this scenario, there are different things that you can do. First is that you can separate this into. So first, I will simplify so you have ln square root of x squared plus 1 divided by x. Then on this one, I can put this one as 2x x squared plus 1 square dx plus 2 x squared plus 1 square dx. So now this part, again, we can use u substitution if you do the same thing here. You use u as x squared plus 1. So what we end up having is that ln of square root of x squared plus 1 divided by absolute value of x. This one I just rewrite it. Now if you put this out, you gotta have du over u squared plus u 2 over x squared plus 1 square. Now this one is where we're going to use trig substitution. So this one is ln square root of x squared plus 1 over absolute value of x plus negative 1 over u plus. Now this part is where you trig sub. So you have x squared plus 1. So the substitution that you're going to use is that you're going to put u as tangent of theta. So du is going to be, actually you put x as tangent theta. So dx is going to be secant square theta d theta. And so what we have here is that we're going to have 2 secant square theta d theta. And in the denominator, you have tangent square plus 1 square. So it's going to be secant square, and then you square again. So it's going to be secant fourth theta. So what we end up having is that ln square root of x squared plus 1 over absolute value of x minus 1 over u here is x squared plus 1 plus 2 over secant square. So you can rewrite as 2 cosine square theta d theta. And here we only need to use the double angle formula to solve the problem. And so I'm not going to proceed further because this should be easy for you. But the final answer, after you get into the form of cosine 2 theta, you have to put it back into the form of x to make this answer valid. And so what I have is that I'm going to have ln of square root x squared plus 1 over absolute value of x minus 1 over x squared plus 1. And so it's going to be so this is 2 over secant square. So what I end up having is that I'm going to have plus half of arctangent or inverse tangent of x plus x over 2 x squared plus 1 plus c. And so this example is a very tedious and very challenging one. If you guys haven't anticipated all of the scenarios that you're going to run into. As you can see, first we use partial fractions to put it into smaller form of fractions where you can easier take integral. Then you have a lot of problems that we're running on. First you have to use substitution twice. Then you have to use trig sub, and then we're going to have to use right triangle relationship to put it back into the form of x. So it's a lot of work that's going on. But this is a very helpful example because I think it's a very good representation of the type of problems and the level of difficulty that you guys gonna run into in the midterm. And so having said that, if you have any questions when you look through this video at home, please feel free to email me. I'll try my best to answer your questions as soon as possible. Now I have the last example, and this is kind of like showing my showing what I say when I say what I mean when I say you don't need to go too hard in some problems. There are problems that you can solve easily without using any kind of technique, and this is one of them. And so here we have the integral of sine minus cosine square times sine 2x dx. And so what we have is that I'm gonna try to see what does this square give us. So sine square plus cosine square first give us 1. And then you have minus sine x, 2 sine x, cosine x. Then you have sine 2x dx. And this part is just 1 minus sine 2x multiplied sine 2x dx. And it gives us sine 2x minus sine square 2x dx. So using the double angle formula, it's going to give us sine 2x minus 1/2 of 1 minus cosine 4x dx. And so this problem can be solved easily by solving each of them individually. So first I'm going to simplify the algebra. So you have negative half plus half cosine 4x dx. And so this one is going to equal to negative half of cosine 2x negative half x plus 1/8 cosine 4x plus c, or negative fourth sine 4x plus c. And that is my final answer for this problem. We don't need to go any further from this. And as you can see, we only need to use the double angle formula for both sine and cosine to solve this problem. And so my message here is that sometimes don't overcomplicate the problem. There are problems that you have to use more than one technique, but there are problems that you don't even need to use any kind of technique. So just do a lot of practice, and you kind of like put yourself into different scenarios, get exposed to it, and then you're gonna figure out the problems yourself. It's gonna take really long when you do these problems, especially before the midterm. But it's better to know these scenarios before the midterm than in the midterm. That time you are under time restrictions. So again, I would say do your practice. And as you can see here in the following slides, I have a lot of practice problems that I collect through my previous exam and also through the courses that I work with Dr. Casher before. So it's very helpful for you to walk through them and kind of like get used to them. I collect these from her previous exam. I trust them a little bit, so it's also good preparation for the exam. And so having said that, if you don't have any further questions, I'll end the meeting here, and I'll see you guys next week. Bye.